Hello, in this video I'll be solving problem 6.13 of David J. Griffiths' Introduction to Electrodynamics, 4th edition. Problem 6.13 reads, suppose the field inside a large piece of magnetic material is B naught, so that H naught is equal to 1 over mu naught multiplied by B naught minus M, where M is a frozen-in magnetization, so it's in that position always. Part A says, now a small spherical cavity is hollowed out of the material. Figure 6.21 shows this, which I've included here. So that's the sphere that we're removing from our material. We want to find the field at the center of the cavity in terms of B naught and M, and also find H at the center of the cavity in terms of H naught and M. To begin this, we'll understand that the magnetic field of a sphere is equal to 2/3 mu naught M. And this is from example 6.1 earlier in the book. So if you want to understand why a sphere is equal to 2/3 mu naught M for the magnetic field, then go back and solve 6.1. Since we're removing this sphere from our material, we're hollowing it out, we're just subtracting the amount of magnetic material that the sphere has. So our new magnetic field for our material is equal to the original field, B naught, minus the sphere's field, which is 2/3 mu naught M. So this is our new magnetic field. We also want to find H at the center of the cavity in terms of H naught and M. And we're given up here that H naught is equal to 1 over mu naught multiplied by B naught minus M. But we're trying to find H. And in general, H is equal to 1 over mu naught times the magnetic field minus M. However, at the center of our cavity, M is equal to 0. So H for our, that's the center of the cavity, is equal to 1 over mu naught times B. So we're going to plug in our new magnetic field to solve for our H with this cavity. So H is equal to 1 over mu naught times B naught minus 2/3 mu naught M. Multiply the 1 over mu naught into the parentheses, and we get that H is equal to 1 over mu naught B naught minus 2/3 M. However, we want to find H in terms of H naught and M, as noted here. So, to do this, we're going to substitute the value for B naught into the equation. From our given, H naught is equal to 1 over mu naught times B naught minus M. Rearranging this formula for B naught's value, we find that B naught is equal to mu naught multiplied by H naught plus M. That's just simple moving terms to the left and multiplying both sides by mu naught. So plugging this into our equation for H, we'll find that H is actually equal to 1 over mu naught times mu naught multiplied by H naught plus M minus 2/3 M, which 1 over mu naught cancels the mu naught inside of the parentheses. So we're left with H is equal to H naught plus M minus 2/3 M, which with simple subtraction, H is equal to H naught plus 1/3 M. And that's the H at the center of our cavity, after removing the magnetic field of 2/3 mu naught M from the material. Part B, we're doing the same again, however, for a long needle-shaped cavity running parallel to M, as seen here. It's running parallel to M. This is M, given there. So I don't know why my pen's acting up. So what we're removing is essentially a long solenoid. Now a solenoid has a magnetic field of mu naught K, and K is equal to M cross N hat. So we want to find N hat and M's direction. So drawing out the solenoid, in the terms given to us, where M is parallel. We can clarify that M is also in the z-hat direction to make things easier. And remember, this is a cavity. This is not a cylinder in open space. All around this cavity is solid material, solid magnetic material of B naught. So in terms of coordinates, S would be in this direction, making this negative S hat. But this is also our N hat. So N hat is equal to negative S hat. Or our normal vector is in the direction of S hat, negative S hat. So when we solve for K, we'll find that M, which is in the Z hat direction, is crossed by negative S hat direction, which Z cross multiplied with negative S hat is equal to negative phi hat. So K ends up equal to M times negative phi hat. So K is traveling around our cavity like this. And with the right-hand rule, we'll see that this actually forms a magnetic field moving downwards. So when we plug this back in, we'll get a B is equal to mu naught times M in the negative phi hat direction. But this is just typically written as B is equal to mu naught M. Now we want to find our new magnetic field of the magnetic material with this removed. So just again subtracting this from B naught, we'll find our new magnetic material's magnetic field. So B is equal to B naught, our original, minus this new value, or not this new value, but this hollowed out value, which is mu naught M. So this is the magnetic field of our material after taking out this long needle-shaped cavity. And to find H, we'll follow the same process as before, writing down the given value of H naught, 1 over mu naught times B naught, I believe minus M, yes. And that in general, H is equal to 1 over mu naught B minus M. But at the center of the cavity where we're finding H, M is equal to 0. So it's 1 over mu naught times B. And this B is our new field. So plugging this in, we get our new H, which is equal to 1 over mu naught times B naught minus mu naught M, which when you multiply the 1 over mu naught into the parentheses, you get that H is equal to 1 over mu naught B naught minus M. Which, if you realize, 1 over mu naught times B naught minus M is equal to our original given formula for H naught. So our new H at the center of our cavity could also be written as equal to H naught. Part C of this problem wants us to do the same for a thin wafer-shaped cavity perpendicular to M. So again, this is just another solenoid in the same direction with the same coordinate plane. So again, N is pointing inwards into this. K would be traveling around in the negative phi hat direction. And this would again produce a B moving in the downward direction. But however, this long solenoid is not long. It's a very short, thin wafer-shaped cavity. So it's a very thin solenoid, which means there's not much current going around the outside of this, compared to this long needle-shaped cavity, which is a solenoid with lots of current going around it. So this magnetic field would be very small. Oh, that's way too much. So this magnetic field produced by this wafer would just be a very small value. So I'll just write this up here. C, the new magnetic field, would just be B minus B naught minus this field, which is, again, equal to mu naught M from our solving down here. Mu naught M. But mu naught M is so small, thanks to such a small amount of current going around it, that B just ends up being about equal to B naught. So this is just our new formula for our magnetic field. To find H at the center of this cavity in terms of H naught and M, again, you'll just find that in general, H is equal to 1 over mu naught B, and typically has minus M there, but M is equal to 0, so that reduces just down to 1 over mu naught times B. And this new magnetic field is just B naught, so it's just B naught. And if we plug in our value for B naught, so that we can find H in terms of H naught and M, we'll find that H is equal to, again, going back, the value for H or B naught from moving around terms is equal to 1 over mu, or just mu naught times H naught plus M. So plugging this in, H is equal to 1 over mu naught times H naught plus M. That's all in parentheses. So multiplying the 1 over mu naught into there, you just cancel out the mu naught on the inside. So H actually ends up equaling H naught plus M. And that's the new H value for this formula at the center of the cavity. And that's how you solve problem 6.13, parts A through C. Thank you so much.